Okay. In this lecture, we're going to go over contacts in SOLIDWORKS and how to define and describe them. Why do we care about contacts? We care about them because we need to accurately represent how parts interact with each other in an assembly. So basically everything that we've done up until this point has been on a single component. When you have assemblies of multiple components, we have to worry about the how to treat the contacts between the two parts, and that's where contacts come in. So you have your global contacts, which are your overall settings, and then you have your local contacts, which are used for specific contact interactions. There are 3 types, but we're really only going to deal with 2, and then we'll learn about a third one later. So the 3 types are bonded, no penetration, and then allow penetration. For bonded, if things are bonded, the surfaces act as if they are rigidly locked together, and you have a compatible mesh, and you merge your nodes. For no penetration, what happens is your 2 faces are free to slide on top of each other, and they're free to separate. So bonded can't separate. They cannot go through each other. So like you can't pass through each other. There's also that would be what allow penetration does. You have shrink fit, shrink fit for interfering components. We're gonna do shrink fit next week, actually. Maybe, might be in a few weeks, but we're gonna do shrink fits. And then one last thing to note is SOLIDWORKS sets your contacts based on surfaces that are touching. So small gaps can cause issues. So like when you're drawing your CAD model to allow for tolerances, if those 2 faces aren't touching, SOLIDWORKS isn't going to automatically find that as a contact, and then if a force is applied to one body, it's not going to transfer to the second body. So you really have to be careful when you model assemblies to make sure all of your contacts are accurately being portrayed. So we're going to make an assembly today of a churn pin. That's a bracket with a pin in it. The first thing we're going to do is create some split lines on this part and then prep it for being modeled. A lot of the models we've worked with previously, this has been done already, but we're going to set this up. So based on the part that we are looking at, I need to put 2 split lines in. So I'm going to insert some reference geometry. I'm going to insert some planes. I'm going to use the right plane as my reference. I know that I need it to be 0.75 inches, and then conveniently we need a second one that is 0.75 inches from the first one. So I can increase my number of planes to 2, and that will create 2 equally spaced planes. So now I have these 2 planes roughly where I need them. I'm going to insert my curve for a split line. I'm going to use the plane and the face, and I'm going to make it an intersection. And then I'm going to select both planes to do it at the same time. So what this does is it allows us to isolate this face that we're going to be using for mating and applying forces to, because we're going to apply the forces over here, not over here. So I'm going to save this, and then we're going to create an assembly. So I'm going to create an assembly from part. I'm going to use this part as the basis of my assembly. There it goes. So over here, SOLIDWORKS is going to show you any parts that you have open, so I can just ploop it in. Then I'm going to insert a component. I want to use an existing part or assembly, and this is only going to show me the parts that I have open, so I'm going to browse, and I'm going to find the base. I'm going to open the base, and I'm going to ploop it over here. So you notice I can move this base around. I can't move this pin around because the first object you put into an assembly becomes fixed. So we're going to put some mates in. We're going to make a concentric mate between the cylindrical faces. You can use any cylindrical face. So you can click up here for mate. SOLIDWORKS likes to guess which kind of mate you wanted. Since I selected 2 circular faces, it wants to make a concentric mate, which is what I want. So now this base can slide along the pin. It can rotate, but it has to remain concentric with the pin. The next thing I want to do is I want to use this right face and this end face, and this is where some mates pop up. I want to use a distance mate. And that distance is 0.25 inches. I need a 0.25 inch gap on my base. And now see that the base can rotate around this pin because the pin was the first component added to this. So I'm going to add one more. So since our assembly has a front, top, and right plane, each part also has a front, top, and right plane. So I'm actually going to make the 2 top planes parallel, and that'll just make sure everything lines up nicely. I'm also going to use this front plane, so I'm going to rotate a view for the front plane. And on the front plane of the assembly, which is up here, not the front plane of the parts, I am going to make a sketch. And I'm going to draw a line. And you need to be very careful. Hold on, I want to exit the sketch. I want to do one more thing. So if here's my origin, just over here randomly. I'm actually going to float my pin, so now I can just move everything. I'm going to take the origin of the pin and the origin of my assembly and make them coincident to line up the planes and to line up our components in our assembly. Now I'm going to put a sketch on the assembly, and I want to draw a line, and I want to use the origin of the part to draw a vertical line. That's all I'm going to do is I'm going to draw a vertical line, because I want to use this vertical line to make an extruded cut. Which is going to be under assembly features. We are going to make an extruded cut. You can see it's showing different arrows that we can use from the extruded cut. We're going to go from this sketch pane, we're going to go through all. You're going to see this plane shows up, so we can go in different directions. Now, we put the split line on the right half, so we want to make sure the left half disappears. So we want to make sure that arrow is pointing to the way that we need it to disappear. And we're going to just select our through all, and we'll cut away half of our model. Let me make sure we cut away the right half. If I have a separate face on the outside and on the inside of our cut model. So we're using symmetry to reduce the overall size of our model so we can make it run faster, because anytime you have contacts, your models are going to take longer to run because it has to calculate what's going on here. So I'm actually going to save this. Just so nothing bad happens. So now we've done all of this work to get our model ready for the actual simulation that we are going to run. So now I'm going to go to simulation. I'm going to make my new study. We're still doing static studies. And now I'm ready to work my way down my feature tree. I'm going to right click on parts. I'm going to apply a material to all. And the material I'm going to apply is cast alloy steel. So now my parts have been defined. I am going to put a fixed geometry on the inside face of our bolt holes. And then I'm actually going to use an advanced fixture called symmetry on all of the cut faces, and as you can see, it's making a projected part show up in yellow. Put some, you can see it showing up. Okay, so now we have symmetry, and we have fixtures, and notice the symmetry is showing translation arrows normal to the plane, because if there was a part there, that side can't move normal to the plane. Next we're going to do the contact. So if you see, if we expand these contacts here, we have a global bonded contact. What we're going to do is put a local contact which will override the global contact between this pin and this base. The easiest way to do that is if we actually go back to our 3D model and click on configurations, not configurations. I'm going to click on view. view. Oh, I forget how to make a exploded view. I'm gonna click on exploded view. There it is. Thank you. We're gonna do a regular step. Our components. We're just gonna push the pin that way. So now we have a exploded view. I'm going to go back to my static study. I'm going to right click on connections, and I am going to create a local interaction. Instead of, I want to manually detect it. I'm going to set it to contact. Contact is going to make a no penetration type boundary between them. The first surface I want to choose is the inside. I'm going to choose the inside face there first. The second face will be the face on the pin. I'm going to click my check mark. So now here we have our global that's bonded, and we have our local that's overriding it. I'm going to go back to my feature tree. And I am going to collapse my exploded view and go back to my simulation. We have our symmetry, we have our fixtures. We're going to put our load on. So this pin experienced a force that, if we're looking at this, goes at a 60-degree angle like this. So we are going to put a force on the circular pin surface, but we don't want it to be normal. We're going to select a direction, and we're going to use any flat face. I'm going to use this inside face, and we need to note our directions here. We want a horizontal going this way and a vertical going that way. And these values are 200 and 346.4. So this was subject to an 800-pound load, but since we're only looking at half the model, we're going to use a 400-pound load, which I broke down into its two components. So now we have our vertical and horizontal components. It's important is the normal component, so anything normal to this face is not a force that we want. And remember, these directions are in reference to this face that I chose. So now that we have our fixtures and our loads, we're going to run a standard mesh. It's going to take a little bit of time because it's got to resolve the contacts. No, you can't mesh it until after you've made your contacts. And you see here it's establishing this matrix, and then it iterated on it. And now it's solving the contact constraints. And this is where it's going to spend a lot of time, because where bonded merges the nodes in contacting areas, no penetration doesn't. So it takes a lot of computational power and effort to solve these contact regions. So the more you have, the longer things are going to take. And and it pops out our results. We have our von Mises plot. So before we look at a graph of contact pressure, we're going to look at the von Mises plot a little bit more. I'm going to show you how to edit some views on it. So if I right click on my von Mises plot, I can make what's called an ISO clipping. What ISO clippings do are, first I'm going to hide the forces and the fixtures because there's junk in my graph. I can use an ISO clipping. What an ISO clipping does, it's only going to show you values in a certain range. So if you notice here, it's now showing you values that are 1391. If I slide it to the left, lower stresses come in. If I slide it to the right, it's only going to show me higher stresses. You can flip this arrow where it works the other way, where it's only showing you things lower than it. We can put 2 on, actually, so I can show you values between this and this. So if I set this first number to, let's say 2032.73, and I set the second number to 418.87, it's going to show you values between those. So it's really good for finding stress equal to a certain value, where the arrows will show you what you're looking at. So this is showing me values above 2373. If I say plot on isosurface only, you're going to only get that value. You're not going to get anything higher. I'm going to turn off the ISO clipping just so it doesn't mess anything up. And again, as a reminder, we can animate our stress by right-clicking and hitting animate. We can change the number of frames, say 10, and then run it again. The more frames, the smoother of a picture that you'll get. Just fun things that happen. You can do the same kind of things with ISO clippings and animation to the displacement and strain plots. We're going to create a new plot in this case to see what's going on with our contact. So I'm going to create a new stress plot, and we're going to make a plot of contact pressure. Notice this only shows up because we have contacts occurring. We're going to show it as a vector plot. So we're going to look at it, and you're going to see these arrows show up. So we're going to actually edit its definition, find its symbol size, definition, show as vector plot. I can't find the setting right now of how to make the symbols larger, but what's unique about a contact pressure plot is it's showing us the magnitude and direction of our contact pressure. You can see it's higher where we applied our forces and our load, and it's lower where it's not. So that's how you can look at some of your contact stresses. We're actually not going to go into verification with this. If we also look back at our von Mises plot, I'm going to pose the question to you of whether or not you think the, I'll get a good view of it. This will work. And if as I animate these, whether or not you think the way that this part is deforming is an accurate representation. So you can pick your brain on that. But yes, this contact pressure plot is showing us the magnitude and direction of the contact pressure for our contact. So we can rotate it around and again see how it's larger where we applied our force on the outside and it's being pulled upwards with that 60-degree angle that was defined. Vector plot option. Vector plot options. 600% is what we're going to make them. We're going to make sure it matches the color so we can actually see the pressure with our vectors. You can go up to 1,000, but there we go. Now we got some arrows we can see. Okay. And again, so this is basically it for this. We're just a brief introduction into contacts. We're not calculating the contact pressure by hand. That's above the scope of this course for this example at least. But what's important is to know we have global contacts and you can define local interactions, because when you're modeling an assembly, you have to make sure you're actually modeling the contact between components correctly. And this is also going to lead us into what we're going to do on Thursday, which is talk about bolts, and into our next project, which is all about bolts.